All right, for this next video, we're going to cover alkylation. And this is a pretty important part because this is going to kind of set the basis for the rest of the chapter in terms of this enolate chemistry. Essentially, alkylations are, they make a new bond between the alpha carbon, right, of our enolate and another electrophilic carbon. Similar to like a grenade in some respects, right? We're making a nucleophilic carbon and it's attacking an electrophilic carbon. So an example real quick, we have our ketone, we have our strong base, sodium hydride, and then we'll include an electrophile. Right, so we'll do this propyl bromide. The product looks like this, where the enolate was, right, that nucleophilic carbon has attacked the propyl bromine. So what does that mechanism look like? Right, not all that dissimilar from the halogenation reactions. We have our strong base here taking away, right, one of these hydrogens to get to our stable enolate here. Again, you could draw this in the other resonance form, and that would be fine by me. And then we do this SN2-like attack, where we have a nucleophilic carbon coming in, kicking out our bromine, right, in this SN2-like reaction, right? We see that? The nucleophilic carbon here is attacking, essentially, the electrophilic carbon there to get to our final product. And we can do this sort of chemistry on multiple different systems. But something I want to talk about now is this process called synthetic equivalent. Kind of like the name implies, it is this way to quote-unquote mask and unmask a reactive species. Mostly due to unwanted side products because of strong bases being present. So the synthetic equivalent of using this acetone, right, this normal acetone, is to use this ethyl acetoacetate, which is effectively this group, because with this, right, we can use weaker bases, right, like what we talked about in the last video, right, because there are two ketones present here, right, they are much more acidic, right, the pKa is lower, it's about 9, versus the pKa for, right, all these hydrogens, the pKa is about 20, so we have to use a much stronger base for an acetone, okay? And despite what the slide says, the reaction we're going to do in here and the mechanism I'm going to do on a different page to give myself more room. So the reaction looks like this. So we take our synthetic equivalent here, right, our acetoester, and we can use, right, a weaker base. So we're going to use this ethoxide, right, which is one of the weaker base options we gave, right, it's a weaker base. And then some sort of electrophile, and the product we get from that would be this, right, very similar to the last reaction we just covered. And from there, right, we want to unmask the this molecule to get back to our original species that we want. So this is in some ways very similar to protecting groups. It effectively is as a protecting group, but it's sort of as a fancier name, right? So it's almost like this whole piece here, right, is the protecting group, right? Because otherwise, right, if we took that off, it looks a lot similar to our acetone, right? So this whole sort of ester here is kind of our protecting group in a sense. So from here, right, to go back to our original, or get to our original quote-unquote acetone-like molecule here, we would do this process where we add in base and water, right, which is hydrolysis, and then we add in H3O plus and heat, and we get to this molecule here, which is just our desired product. You see that? So this whole group here has left. So this is our leaving group here. So how has this happened? And I will actually add this here too, right? It happens due to a loss of CO2, essentially. Okay, so let's take a look at how this happens. So I'm going to go to another page, again, to do the mechanism, but this is all still related here, okay? If you have room, go for it, but I'm using a different page here. So the mechanism looks like this. So I'm going to start from that first product, okay, where we have done our alkylation, right? The alkylation is done, right? We have that propyl group there. And so I'm going to split up the next part into two steps, right? That step number one we had on the last page was this hydrolysis. Right, remember, this hydrolysis is what lets us turn esters to carboxylic acids, right? Saponification, you could also say, right? Or, sorry, carboxylic acid. Okay, so, right, we do this mechanism, right? Our base comes through, and I'll do a sort of shortened mechanism here just to show you. Right, our base comes through, right, we form our tetrahedral intermediate, the ester leaves as a leaving group, and we're left with our carboxylic acid, right? And so from here is where the magic happens. So I'm going to draw this molecule in a slightly different way for step number 2. Probably shouldn't use an arrow here. I'll just draw it down below so you can see what I mean. Right, notice it's still the carboxylic acid. I've just rotated that middle bond, right? And so from here, this is where the next step happens, and this is due to that second step, right? With acid, and primarily this factor here, heat, is what allows this to happen, okay? So the reaction here looks like this, and we'll do this in red here. I'll also draw this hydrogen differently. Right, there's this light hydrogen bonding happening here, so the hydrogen is sort of positioned appropriately there. And so the mechanism looks like this. Our carbonyl is going to want to grab that hydrogen. These electrons are going to fall down, and we're going to put the covalent bond here, and our electrons come up here, okay? So we follow the electrons very closely, right? We can see that the following transformation has happened, where we are in the enol form, right on the left side. We have formed the alkene, and then we have the rest of our propyl group attached to the alkene, right? Right, so those 3 carbons are there, and we have lost CO2. And the reason why this reaction happens, right, so well is because, right, CO2 is a gas. So when it leaves a solution, it's a really, really forward-driven reaction, right? Le Chatelier's principle kind of tells us that, right? So because CO2 is left, it makes this reaction particularly good, right? And we can see, to highlight here as well, right, this is where CO2 has come from, right, what I've just highlighted here. Okay, and we have our enol, but we know, right, there's water present in this reaction. We can do this tautomerization, right, to get to the desired ketone form. Okay, so let's look at another example of this. So another example of this is the malonic ester synthesis. So very similar, right? This malonic ester, or this diethyl malonate, is the synthetic equivalent for acetic acid, right? And it's important, right? Especially this acetic acid bit is important because, right, and you can see it here. We can't do carboxylic acid enolate chemistry due to acid presence, right? Because if we try to expose this to a base, right, we would just deprotonate our OH there, right? So that wouldn't work. So we can't do traditional enolate chemistry on carboxylic acids. So we have to resort to using this diethyl malonate. So what does this look like? Again, this is also, right, another example of this synthetic equivalence, right? This masking and then eventually unmasking process. Again, very similar to protecting groups. So we start with our diethyl malonate. And again, because of these being really, right, more acidic, right, lower pKa, we can just use a weak base. Right, we don't need to use those sodium hydride or that LDA like we talked about in the last video. And we get to the following alkylation step, right, where our nucleophilic carbon has attacked our electrophilic carbon, right, to get to our ethyl group here. And from here, we can do this, again, same exact process as the last page, where we do this hydrolysis first. So sodium hydroxide or potassium hydroxide, whatever, right? This hydrolysis step, and we get to, and I will say this is right in excess, so there's a lot of equivalents of this. So we end up doing not just one hydrolysis or saponification, but two. So it happens on both sides here. Both of those esters become carboxylic acids. And then in the final step, right, same exact process where we are losing CO2, we're going to do this H3O plus and then heat, right, to the same sort of chemistry where we're going to lose CO2 essentially to get to as our final product, the carboxylic acid plus, right, CO2. Right, and again, we can see our 1, 2, 3, 4 carbons here, 1, 2, 3, 4 carbons here, right, with that leaving group, right, which will be CO2 after this sort of rearrangement happens. We get to the final carboxylic acid, right? And again, we wouldn't be able to do this sort of chemistry, just to really reiterate here, we couldn't do the same chemistry with this molecule because, right, if we tried exposing to these same conditions, right, if we did this, and then 2, right, what would end up happening, right, is this would get deprotonated, and then we would do the SN2 reaction with this molecule, so we'd end up forming the ester instead of, right, the enolate chemistry. So we have to do this diethyl malonate sort of situation, right? We have to mask, we're sort of masking the sort of right half here and then taking it off at the end to get to the right desired product. So we'll look at more examples of this in class as well. This masking and unmasking process, again, very similar to protective group chemistry, very important for, right, an actual synthetic chemist because we have to worry about things like this being too acidic and this not being acidic enough.